Okay, welcome to section 4.3, driving permanent magnet DC motors, PMDC motors. This is a section from the Real-Time Computing for Mechanical Engineers book with Garbini and Devine. I'm Dr. Piccone. I published this book with MIT Press, and here is the companion website for the book, rtcbook.org. Okay, driving PMDC motors. The collection of electronics that supplies power to the motor is called the motor amplifier or motor driver. The way this works for AC motors is quite different than for direct current or DC motors. The different types of DC motors also require different types of amplifiers. So, for simplicity, our discussion here will be limited to the driving of PMDC motors, still a large class of motors. To propel most mechanical loads, a motor requires significant electrical power. A computer, typically a single-board computer, is used to control the motor in most cases, but it can supply only milliwatts of power, so we will need a motor amplifier. Electrical power electronics engineering has devised a number of excellent options, such as the power op-amp and power transistors. These and other power electronics can be controlled by a computer. The figure below shows a motor amplifier in a typical configuration. A computer supplies a variable control signal to the amplifier. So here's the computer supplying a variable control signal to the amplifier, which draws power from the supply to provide the motor with controlled power. So the amplifier draws power from the power supply, and controlled power is what the amplifier supplies to the motor. Okay, so that is the typical configuration of a motor amplifier, a controlling computer, and a power supply for the amplifier. Motor amplifier variations. A motor amplifier supplies electrical power to the system. The output voltage of an ideal voltage amplifier is controlled to be proportional to its input. The output current depends on the connected load. The output current of an ideal current amplifier is controlled to be proportional to its input. The output voltage depends on the connected load. In the system models of section 4.1, the voltage source, Vs, models a voltage amplifier, and the current source, Is, models a current amplifier. The input of a motor amplifier can be either analog or digital signals, typically from a computer. The output can be either analog or switched, i.e. turned on and off at a high rate. Typically, a motor amplifier with an analog input will supply an analog output, and one with a digital input will supply a switched output. We consider the analog input, analog output case in section 4.3.2, this lecture, and the digital input switched output case in section 4.3.3, also later on in this lecture. Finally, the motor amplifier input signals can be either voltage signals or current signals. The former is called a voltage-controlled amplifier, and the latter a current-controlled amplifier. There are several possible combinations of motor amplifier input and output, some more common than others, which are summarized in table 4.1. So, on the input side, we have analog or digital possible, and we also have voltage or current controlled possible on the input side. On the output side, we have analog, so it could be analog output or it could be a switched output, and the output could be voltage or current, some controlled voltage or some controlled current. So for instance, a digital voltage-controlled switched voltage amplifier is a common variety. So digital voltage-controlled switched voltage amplifier is a common varietal. There are others, and we'll also see the analog input, analog output case later in this section. Okay, the challenges of driving motors. We now consider 3 challenges of driving PMDC motors: inductive load kickback, power sinking, and current spikes or current transients due to the back EMF effect of the motor on the driving circuit. When designing with the amplifiers considered in the sections that follow, these challenges are frequently encountered, so we're going to take a look at them so that we understand them here. Inductive load kickback. The easiest design scenario for motor driving is when the motor needs to spin in only a single direction. Here, the most significant challenges are because the motor is an inductive load, i.e., it has significant inductance. This can cause an issue even for driving in a single direction. If the amplifier suddenly changes the current flowing through the motor, an inductive kickback voltage is observed with this inductor elemental equation, which says that the voltage across the inductor is proportional to the time rate of change of the current through the inductor. So if the amplifier suddenly changes the current, say turning the current off or turning the current on suddenly, this term gets very large, the time rate of change gets very large, and therefore so does the voltage across that inductor. Amplifiers must be protected against this voltage spike. Typically, this can be handled with a high-speed diode from the amplifier output to its positive source and one from the negative source to the amplifier output. The diodes switch on until the voltage returns to normal. So we get this large voltage spike, those diodes will kick on and release that voltage. Power sinking, the second complication when driving motors. To control the position of the output of the motor or to control its speed in both directions, one must be able to apply both positive and negative voltage and current. Typically, power comes to the amplifier from a differential supply with positive, negative, and ground terminals. Here, the inductive load comes back to haunt us again. If the amplifier suddenly changes the direction of the voltage applied to the motor, the same equation shows that the current will change slower than the voltage does. So this equation again, the elemental equation for an inductor, says that when the voltage changes suddenly, the current starts to change, but it doesn't change instantaneously. It changes with some rate governed by the voltage. So the current will change slower than the voltage does. And the larger the inductance, the slower this change in the current. That seems fine, but the trouble is that the source will have to act as a power sink, absorbing energy instead of delivering it. Consider the circuit of figure 4.4a, shown here, which has an inductive load L and resistance R, similar to a motor's armature. So we don't have a full motor model here, just a resistance and an inductance, no mechanical side. We can derive the governing differential equation in inductor current IL to be the following first order differential equation. For a voltage step input, Vs equals kappa US, where US is the unit step input, and initial current IL of 0, the current response is given here, which is to say the initial current times this decaying exponential plus this exponential that decays to kappa over R. So this is a solution for the inductor current as a function of time, given a step input of magnitude kappa volts. The 4 quadrants. To model a step from positive Vs to negative, or vice versa, we set IL of 0 equal to negative kappa over R. That is the negative of the steady state step response. Equation 4 becomes IL of t equals kappa over R times 1 minus 2 e to the negative RT over L. This is equal to the source current IS shown below, twice. The current will have its original sign right after the reversal. The source power, Vs Is, is therefore negative for an interval of time, which implies that the source is acting as a power sink. So we see here plotted the source voltage Vs of t in orange with the orange axis here. And we see the current Is of t that's drawn by the circuit also as a function of time in blue and with the scale associated with the right-hand blue axis. We have normalized time. Time is being normalized by this time constant, L over R. And we see that the voltage changes instantaneously and the current lags behind. The current lags behind, so that when we have a switch from a positive voltage to a negative voltage, the current is still positive for a while. A positive current multiplying a negative voltage is going to result in a negative power, which is a power that the source is sinking from the circuit. Finally, it catches up and the current and the voltage have the same sign, in which case, once again, the supply is supplying power to the circuit. We do another reversal here to see this in action again. Whenever we flip the sign of the voltage and we let the circuit come back to steady state, we'll see this lagging behind current. Setting IL of t equal to 0 in equation 6, we get the time at which this occurs corresponds to about 0.7 times L over R. We see that the larger the inductance, the longer it takes for the current through the motor to reverse. So this is the crossover point when power goes from negative to positive when we do a reversal of voltage. Note also that this does not depend on the magnitude kappa of the step. With some small motor values of R equal 1 ohm and L equal 1 millihenry, the current reverses in just under 1 millisecond. This may not sound like very long, but a motor amplifier can be damaged in that time if it is not able to absorb the negative power. There are 4 quadrants that can be demanded of a power supply: Vs greater than 0 and Is greater than 0, same sign. Vs less than 0, Is greater than 0, opposite signs. Vs less than 0, Is less than 0, same sign again, both negative. And Vs greater than 0, Is less than 0, opposite signs. The figure below illustrates the 4 quadrants: supplied current positive on the right, supplied voltage positive on top. We have the 4 quadrants being positive power, negative power, positive power, negative power. Okay, those are the 4 quadrants. In 2 of the quadrants, the source is supplying power to the circuit. In 2 of the quadrants, the source is sinking power from the circuit. Current transients from driving voltage, steps, and back EMF. This is the 3rd challenge in driving motors. As we have seen, the dynamics of the electrical and mechanical sides of a motor are coupled. The electrical power supplied to a motor cannot simply be treated as independent from the motor or from the mechanical system to which it is connected. The inductive load causes voltage spikes when the input current is stepped. Conversely, the mechanical system's influence on the circuit causes current spikes when the input voltage is stepped. With reference to the voltage source motor model of section 4.1.1, we will now consider the current draw demanded of the source when its voltage is stepped. When the rotor is spinning, an electromotive force called the back EMF subtractively reduces the effect of the applied voltage. This is modeled by the transducer voltage Vm, which is tied to the motor velocity omega m with the motor constant Km. That is, Vm equals Km times omega m. When the voltage source is reversed, the shaft is still moving with its previous velocity. The voltage loop is Vs, which we've just reversed, equals Vr plus Vm, which we haven't reversed the current's still flowing in the same direction. So this voltage drop is the same. The back EMF, not reversed, plus VL. Therefore, the inductor voltage VL compensates for the Vs voltage reversal. For instance, if Vs equals 24 volts, Vr equals 1 volt, and Vm equals 20 volts, then Vs is reversed, and this situation obtains. We have VL equals negative 24 Vs volts, minus 20, which is from the back EMF, minus 1, which is the resistance voltage drop, to give us negative 45 volts. This negative 45 volts drives a rapid current change governed by the inductor equation, which again is dIL dt equals 1 over L VL. So VL drives a rapid current change due to that negative 45 volts. Therefore, both the voltage reversal and the back EMF contribute to the transient current response. As we have seen, if Vs is reversed, this implies that the amplifier must sink power. That was the situation we just looked at. The rapidity of the change due to the back EMF is actually helpful in this regard, since it reduces the amount of time the amplifier must sink power. So this rapid change in the current is actually getting us to a point where the supply is once again flowing positive power into the circuit. We don't have to sink more power into the source. So let's look at this. Here's the problem. Using the voltage source model with the motor and load specifications listed here, simulate the source current IS, inductance voltage VL, and load angular velocity omega j, responses to a voltage step Vs equals kappa US, the unit step function, volts, followed by a voltage reversal. Here's the solution. Parameters for a small 48 volt DC motor and load are supplied here, R being 24 ohms, L being 22 millihenries, the Km motor constant being about 70 millinewton meters per amp, J, the inertia being 2.17 kilogram meters squared, and B being 21.3 micronewton meter seconds per radian. The transfer functions for input Vs to the three outputs Is, VL, and omega j are as follows, derived from the voltage source model from section 4.1.1. The transfer function from Vs to Is equals IL is given with this transfer function, where we have two poles and a single zero, where from equation 4.12, we have the natural frequency being 335 radians per second, and the damping ratio being about 1.63. The transfer function VL over Vs is closely related, so again, it's always going to be the same denominator of the transfer function, and we have two zeros in this case for VL. Finally, we have omega j over Vs, this transfer function, which has no zeros. These transfer functions can be simulated to find the responses. Alternatively, the state equation and an augmented output equation can be simulated directly. Examining the transfer functions, the S in the numerator of Is over Vs is one way of understanding the current's eagerness. A zero will drive a fast change in current Is for a step in Vs. The two zeros, VL over Vs, cause a theoretically instantaneous change in VL, followed by a fast decay for a step in Vs. The numerator of the angular velocity over voltage transfer function, however, has no zeros, and the load angular velocity will respond slowly to a step in Vs. Okay, the solution continued. The current Is response to a voltage step followed by a voltage reversal is shown in the upper figure here and in the lower figure below. These are just different quantities plotted for the same simulation. In the upper figure, we have the source voltage Vs and the source current Is plotted on the two vertical axes. So orange being the source voltage and blue being the source current. We have the source voltage step and then reversal. We see a current transient in the step that started from 0, and then the reversal is the more extreme situation where we have a current transient that's twice as big here. And in the second graph, we have the inductive voltage, VL, in purple, and in teal, we have the angular velocity, omega j. So we see the angular velocity spinning up for the positive voltage application, coming to approximately steady state, and then the voltage reversal, which slowly changes the angular velocity, but the voltage transient, we see the spike here that we described. So the current reaches about 1.6 kappa R amps. So a reversal of 48 volts to negative 48 volts would draw about 3.2 amps. If a full input voltage reversal is required for the design, a driver should be selected that can deliver 3.2 amps for about 1 unit of time. According to the figure, this is about 19 milliseconds. For the small motor, 4 amps may exceed the current rating. A maximum continuous current rating is usually much lower than the peak current rating. The corresponding inductance voltage, VL, and load angular velocity, omega j, responses are shown in the lower figure. In about 5 time units, 94 milliseconds, the angular velocity approaches steady state. At the reversal, an instantaneous jump in the inductive voltage is observed. So that's this peak that we predicted. This is connected to the back EMF, as we saw in the argument immediately preceding the example. The current transient here we can think of as being caused by this voltage transient, which is in turn caused by the back EMF. Okay, so this concludes the third of the 3 challenges to driving DC motors, and we'll keep these in mind as we go through the rest of this section, in which we describe how motors are actually driven by motor amplifiers. The first class of motor amplifiers we'll consider is the linear motor amplifiers class. How can we deliver an adjustable voltage or current? We might think that the analog outputs of a computer provide a simple solution. They are adjustable after all. There are a few limitations to such a strategy. The most important of these is that a computer can supply almost no power through its analog outputs. The voltage range of the analog outputs is usually too small as well, and finally, the voltage range of the analog outputs is typically only positive, so we can't get negative voltage out of many of the analog outputs that are given in single board computers. To drive a PMDC motor in both directions, we need to be able to supply both positive and negative voltage or current, ideally in the full range that the motor allows. Let us call the 3 limitations that we have identified power, range, and offset limitations. So these 3 limitations. So if simply using a computer's analog output to drive a motor won't work, what can we do? The traditional approach is to use a linear amplifier to overcome the power and range limitations. Amplifiers can usually approximate a voltage-controlled ideal voltage source or a voltage-controlled ideal current source within certain power limitations. In general, an amplifier will draw very little power from a computer or other controlling voltage, instead drawing its power from a separate and external DC power supply, like we saw at the beginning of this section. Power transistor amplifiers without feedback. A simple example. So this is the first kind we're going to look at. First example. Analog amplifiers typically include one or more power transistors. Consider the circuit of the figure, this guy right here. This is one of the most basic power transistor circuits for driving a motor. The transistor, which is given here, so C, B, and E. The transistor is an NPN bipolar junction transistor, or BJT. To quickly review NPN BJT operation, which we'll do in more detail in section 5.6 if you want to go there for a more detailed explanation. Under the right conditions, the base B current, so this is the base B current, IB. So under the right conditions, the base B current, which flows from B to E, controls a much larger current, IC, from the collector, C, to the emitter, E. So this current right here is IC. In this circuit, a small control signal, VI, is converted to a current, IB, with resistor RS. We can think of resistors as converting voltages to currents. So we have this voltage VI that's converted to a current, IB, with resistor RS. A positive power supply, VCC, delivers current IC through the motor, M. So here is positive power, VCC. So VCC could be, say, 24 volts or something like that. The 24 volts drives the current through the motor and into the transistor. So this current is controlled by this current. The IB current controls the IC current, which is also the current that goes through the motor. In normal operation, this diode is off, so there's no current flowing through this path. The suppression diode, which we just highlighted, protects the transistor from the motor's inductive kickback when current is suddenly switched, ensuring that VCC plus 0.6 volts is the maximum voltage at the collector. So if we do suddenly change the current, we get a large voltage spike, we will bleed off that voltage by the suppression diode turning on. The primary limitation of this circuit is that the motor can be driven in only one direction, making it inappropriate for speed control in two directions and for position control. The BJT can be somewhat linear, i.e., IC can be approximately beta times IB for constant beta in its normal active mode, allowing the amplifier circuit to approximate an ideal current-controlled current source. However, beta is an unreliable parameter that varies with temperature and can even be a function of IC, so it's not really an ideal current-controlled current source, but it can approximate it in a pinch in certain applications. Another type of power transistor amplifier without feedback, the push-pull amplifier. The amplifier circuit shown in the figure over here is called a push-pull amplifier. This name comes from the fact that current is being pushed or pulled through the motor, and we'll see what pushed and pulled mean in a moment. When the control signal from VI is positive, the NPN BJT Q1 is active and flowing current, and the PNP BJT Q2 is off. So when VI is positive, so there's VI, it's controlling both of these BJTs, one of them NPN, one of them PNP. When VI is positive, we'll be controlling Q1, which is going to be active, and we'll be pushing current from VCC through Q1 and the motor. In the case that VI is negative, Q2 will be active and we'll be pulling current through the motor this direction. So we'll be able to drive the motor in either direction. The inductance of the motor again requires diodes to protect the transistors. Here we have placed flyback diodes. So here's a flyback diode and here's a second flyback diode on each transistor to ensure that they remain either off or active mode and are not subjected to breakdown voltage. Okay, so that's a push-pull amplifier. The two significant limitations of the push-pull amplifier are it has the same nonlinearities as the other transistor amplifier. So just like before, our beta parameter is not great for transistors. It has an additional nonlinearity. There is a small voltage or magnitude drop between the input and output signals of the transistor, about 0.6 volts. This means there is a dead zone in the range negative 0.6 to positive 0.6 volts. This is called crossover distortion, and it can be mitigated somewhat by biasing the transistors. Unfortunately, it's at the worst spot. We would like to do a lot of things near 0 volts, and there's a dead zone in our amplifier there. This is one of the most significant limitations of the push-pull amplifier. Okay, some general considerations with power transistor amplifiers. BJT-based amplifiers can be rather nonlinear. Nonlinearity is generally not a desirable quality in an amplifier. Motor amplifiers are no different. No matter the type of power transistor, BJT, JFET, or MOSFET, it turns out that linearity is much more achievable when there is a connection from the output to the input. This is called feedback. We're going to talk a lot about it. Some analog amplifiers draw significant quiescent current flowing through their output transistors that is simply dissipated to heat. These amplifiers are sometimes called Class A, and they are rarely used for power-intensive applications like motor driving. A push-pull output stage improves the power losses seen in a Class A amplifier, and amplifiers like this are called Class B. Class B amplifiers are subject to crossover distortion, a nonlinear response at low voltage magnitudes, just like we saw a moment ago. This has led to the Class AB amplifier, which allows one to balance the inefficiencies of the Class A and the crossover distortion of the Class B. The Class AB amplifier is just a Class B amplifier in which the transistors have been biased to mitigate crossover distortion. Okay, the next class of linear amplifiers, op-amp amplifiers. So first we'll start off with a power op-amp. The operational amplifier, op-amp, is an amplifier that is exceptionally linear below saturation. An op-amp is actually comprised of several transistors and typically packaged as an integrated circuit, IC. A traditional op-amp still cannot produce enough power to drive any but a very small motor and loads. It is common to see an op-amp paired with push-pull transistor output stage to boost its power, as we will consider in a moment. However, more recently, power op-amps have become available that can deliver enough power to drive a small motor without an additional output stage, as shown in the figure at right. Applying the canonical rule of op-amps that the ideal op-amp in feedback will, as long as it does not saturate its output, drive the inverting negative and non-inverting plus terminals to the same voltage. In steady state, we see that VR, the voltage across the resistor, is approximately equal to VI because these two terminals are at approximately the same voltage when there is a feedback connection like we have here. From another op-amp rule, the input terminals draw no current. Remember, these terminals draw insignificant amounts of current. And Ohm's and Kirchhoff's laws, we find that IM is approximately equal to IR. So here's the motor current IM. And since there's really no current flowing that way, all of that motor current has to flow through the resistor. So IM equals IR approximately. And VR over R is Ohm's law for a resistor. And substituting in the fact that VI is approximately equal to VR, which we wrote down here, we have that the motor current is approximately equal to the input voltage divided by R. Therefore, the circuit is in a voltage-controlled current source configuration. However, others can be used, such as the inverting amplifier and non-inverting amplifier configurations. Okay, some application notes on power op-amps. Like the push-pull amplifier, the power op-amp amplifier can drive the motor in either direction. However, the op-amp amplifier can be more reliably linear than the push-pull amplifier. The op-amp amplifier circuit doesn't show any inductive kickback protection in the circuit diagram, which is sometimes included in the op-amp, but should otherwise be added from the output to VCC and from VEE to the output. It is often important to place a resistor at the output of the op-amp to limit its output current, something that most op-amp specification sheets will clearly describe. Furthermore, the transistor amplifiers described previously and the op-amp amplifier will need help with dissipating heat via a heat sink. Again, the specification sheet will usually provide guidance for heat sinking requirements based on expected use. So that concludes the power op-amp description, and now we'll move on to another op-amp amplifier, a power-boosted op-amp. The power limitations of the ordinary op-amp can be overcome with a power booster stage comprised of one or more power transistors. For position and two-directional speed control, the push-pull configuration is required as shown in the figure. So here we have a regular op-amp instead of a power op-amp. So this is the same output stage that we saw previously, but this time we're controlling it with an op-amp. The output stage drives the motor, and we have a resistor here that goes to ground. What about the push-pull stage's crossover distortion? Do we still have that? The feedback loop will pretty much mitigate the distortion. So the fact that we have feedback here to the inputs of the op-amp, it will actually mitigate that crossover distortion that we had in the power transistor amplifier with this same output stage that we are using now. But now that we have feedback, we'll pretty much have that crossover distortion fixed for us. That said, it is still best to bias these transistors before using feedback and relying on feedback. A power boosted op-amp is capable of much more power than a power op-amp. So in higher powered motor applications, we'll almost always use this instead of a power op-amp. From linear to switched amplifiers are two major classes of amplifiers. For decades, linear motor amplifiers were the most common amplifiers for speed and position motor control. However, in many applications, they have been replaced by switched motor amplifiers, which use a very different approach that we'll now consider. The two types of amplifiers are compared at the end of the section. The primary reasons why switched motor amplifiers have overtaken linear amplifiers is that they are inexpensive and that they are generally more efficient, and therefore they present fewer heat dissipation challenges. And we'll look at some of the other similarities and differences at the end. Okay, pulse-controlled switched motor amplifiers. The switched motor amplifier has at its core one or more switched transistors, usually the MOSFET. We're going to talk more about MOSFETs in section 5.6, so if you wanted to go review the details there, you can. A MOSFET is not nearly as linear in its active mode as the BJT. However, in a switched amplifier, the MOSFET acts as a switch, turning on and off the power from an external DC supply. So we don't operate it at varying levels. We operate it only in on or off position. The switch is controlled by a digital signal, typically from a computer. So the output of a digital amplifier is essentially a voltage or current pulse wave, as shown in the figure right here. The pulse has amplitude A, so we see the amplitude of the signal in blue, pulse width W, period T, duty cycle delta equals W over T, so W divided by T is the duty cycle, and the mean is A times delta, which you can make a geometric argument for. The duty cycle can be adjusted by varying either pulse width W, called pulse width modulation, or PWM, or less commonly pulse frequency, called pulse frequency modulation, PFM. But in what sense is the switched power adjustable DC? So PWM is what we'll use in many cases, but in what sense is this PWM signal adjustable DC? The key is that the electromechanical system that the amplifier is driving, the motor with a mechanical load, has a frequency response that effectively averages the pulse wave, okay? So even though we're putting in the blue line, okay, the mean value, the purple line, delta times A, is approximately the effect that we have. So if we have that effect, we can just change the duty cycle, so the fraction W over T, and we can effectively vary the mean value that's applied. But we need to understand that a little bit better. Why is it that the average is what we get as an effect and not simply a bunch of pulses? Okay, so the PWM and the averaging effect at high frequencies. Consider the figure, which shows simulated responses of the voltage source motor model of section 4.1.1 with parameters from specific target system T1A to a pulse wave input and duty cycle of 0.5 and a few angular frequencies, omega equals 2 pi over T. So what we've done here is show the step response in teal. Okay, so the step response when we apply mu times the unit step function, we see that the angular velocity of the motor spins up to this steady state value, or close to the steady state value, in 20 units of normalized time. Okay, so that's when we just apply a constant DC value. Instead of applying a constant DC value, we're going to apply these different pulse waves, which all have the same average value as the unit step function has. Okay, they all have the same average value. We're just increasing the frequency at which we apply these pulses. The same duty cycle of 50%. And what we see is that as we increase the frequency of the pulse, so first we put in a long pulse in blue, and we wait, and then we put in a long pulse, and we see the motor speed up and then slow down, and then speed up and then slow down. If we keep increasing the frequency in orange, we see that it speeds up and slows down, but it stays closer to this average line. As we keep increasing that frequency, we converge toward this continuous line of a unit step response. So if we have a high enough frequency for our PWM signal, we can get a response that looks essentially as if we had put in a continuous DC value instead of a pulsed value. So this is the power of PWM. As long as the load that you're applying the PWM to has an averaging effect on high frequency inputs, you can get away with varying the input average value by changing the duty cycle of the PWM signal. Okay, H-bridge circuits. A linear motor amplifier can easily supply both positive and negative voltage or current. So that was really nice. Now we're in the switched amplifier case. How can we do that? With a switched amplifier, using PWM, an H-bridge circuit is required. Although this is often integrated into the switched amplifier itself, we need to understand how it works in order to properly design with these amplifiers. An H-bridge is able to switch the direction of rotation of a motor. The four MOSFETs, S, I, J, form a bridge. So we have our voltage supply from the top of the diagram to the bottom of the diagram, and we have the motor here in the middle providing this horizontal bar on the H. Okay, so you see the big H here. This is our H bridge. Okay, so we have four transistors, four MOSFETs that comprise the legs of this bridge. So what we have here are four different states of the same H-bridge configuration, and we have different switches turned on and off at different states. So in this first one, in A, we're in what we would call the drive forward state, which is switch 1-1 is on and switch 2-2 is on, meaning conducting. So these MOSFETs are turned on, so they'll be flowing current through them. The other two are switched off. So VS will drive a current this way through the motor. Okay, now that is the drive forward configuration. So turn on switches 1-1 and 2-2, turn off 1-2 and 2-1, and we'll drive with the current through the motor this way. Similarly, but conversely, we will drive the motor in the other direction with 2-1 and 1-2 on, so the current will flow this way through the motor. So we were able to switch which direction the current flows through the motor by changing which MOSFETs are turned on. There are also these two possibilities, break high and break low. So in break high, we turn switches 1-1 and 1-2 on and 2-1 and 2-2 off, which makes current flow around in this circuit. And similarly, you can break to low as well. And these two states are called break states because there will be current flowing around, so there will be resistive heating and therefore energy dissipation from the system. There will also be mechanical energy losses as well because there will be bearing damping on the mechanical side. So these are called break states, where we allow current to flow and we allow the mechanical system to dissipate energy. And we have body diodes on each of the MOSFETs, which allows current to flow against the direction of the MOSFET. So when we're in the break state, for instance, we're able to have current flowing against the direction of the MOSFET. So that's how we drive a motor with a switched supply in both directions. In forward direction with this configuration, reverse direction with this configuration, and we can also break with these other two configurations. There are additional states. You can also open up all the switches, and that's called a coast state, but we'll ignore that detail for this lecture video, but in the book it talks about it a little bit, so check that out. Also note these are not regenerative braking states. That's another possibility though. So if you're wondering if this is regenerative braking, it's not. The book talks more about it though. Okay, let's compare linear and switched motor amplifiers, which we now understand were pros. A comparison between switched and linear motor amplifiers is given in the table. So By feature, in the first column, we have switched amplifiers in the second column and linear amplifiers in the third column. Switched amplifiers are generally less expensive than linear amplifiers. So the switched amplifier is cheaper and the linear amplifier is more expensive. Switched amplifiers generate significantly more signal noise in the environment, which can be problematic for nearby sensitive electronics. So that's something to keep in mind, that switched amplifiers are noisy, whereas linear amplifiers are less noisy. Switched amplifiers can even generate audible noise if the switching frequency is too low, which is annoying. Linear amplifiers are generally much better at driving a motor at low power, and this is one reason why they are better for high precision motor control. Higher power consumption and heat generation occur for a linear amplifier. Finally, an H-bridge is required for a switched amplifier, and it is not required for a linear amplifier. Okay, so that brings us to the end of the lecture on driving motors. So motor amplifiers, the book section goes into somewhat more detail than we've covered here, but we've got enough to understand how our system works. So that covers linear and switched motor amplifiers. Now that we've got somewhat of an idea on how we drive motors with linear amplifiers, with switched amplifiers, we'll be able to look later in the chapter to applying this to our target system. I'll see you next time.